Okay, hello, this is Patrick O'Shaughnessy. I've developed these modules on statistical methods for analyzing data obtained in the lab or field. And in this short module, we'll focus specifically on the use of graphs for which a log scale is appropriate. And so that will get started. Here again is the module map as we described in the first module. You can see here that I put using log scale graphs to the right of graphing techniques, which means that I don't consider it to be essential for understanding the regression model as you're going down the page here. But it's very useful if you need a reminder on what log scaling is and how to utilize it in graphing techniques. Okay, now we will discuss the use of log scaling on graphs. This may be something you're completely familiar with, but it's worth going over if you're not. So recall that a logarithm is a way to transform one number into another number. So the natural log of e to the x is equal to x. The log base 10 of 10 to the x is x. So for an example, as shown here, 10 squared is equal to 100. So the log of 100 is the log of 10 squared, which is equal to 2. So for example, if you have an exponential increase in values, you can see these are all magnitudes of 10, and we apply a numerical transformation by taking their log value, right? We end up with a linear increase instead of an exponential increase. This is exactly why this was invented, because it was a lot easier back in the day to deal with addition than it was multiplication, or these large numbers. So how do we take advantage of that when we're graphing? Well, for example, there are two types of mathematical relationships for which log graphs are applicable, and many others as well. But the first one is called the exponential relationship. And yes, it can be e to the x. But here you see the simplest form of it is y equals some constant b times some constant a to the x. And again, the a could be the e exponential as well. So we want to turn this or see how it can be developed as a linear function in the form of y equals b plus ax. So the way to do that is to start taking the logs of both sides to cause that transformation to occur. So the first thing to do is, again, take logs of both sides. You can see that on the right you have to bracket the entire expression, and then you can start applying some properties of logs by, for example, the multiplication within the brackets can turn into addition when you pull it out, as shown here. One last thing is that log of a to the x is equal to x log of a. So now we do have a function that is a linear relationship. There are logged values rather than the actual value, but you can see that they are all the original values times their log, except for x here. So you'll see then that x is in its natural form. I can put it around this way just to have it in the same form as shown above. So when you have an exponential relationship, or one with that type of formulation, you end up with what we call kind of the normal value of x is linear in relation to the logged value of the y's. Okay. So let's say we have a graph of values expressed as in the same way as that function, y equals b a to the x. Now if we take the log of the y values and plot them versus the normal values of x, you can see how the values plot as a straight line. So this is what we call a numeric transformation. I had to first take the y values and then compute their log values, which can be easily done in Excel using the log function. And then plot those, but you see you end up with the log of y on the y-axis, which is hard to, for someone to kind of do the math themselves, like what is the real number associated with a log of y being 1.5 For 2, I understand that's equal to 100, right? And 3 is 1,000, etc., as shown here. But wouldn't it be nicer to have the scaling back to normal looking values? Well, that's what log scaling does. It is a special type of graph paper, as shown here, where now we're allowed to plot y's as their real numbers, as 100, as 1,000, on this type of graph paper against the normal x that also gives a linear increase, as shown here. Now, that's not to confuse people that the relationship is linear, but it allows for the development of information, say between 2 and 4 here. You can start picking off what these values are as versus the original value up here. It's very difficult to know what is, the increase here between 2 and 4. So that's the other added benefit of being able to understand the values associated with them by reading them off. So that is an example of what's called a semi-log paper. Half of it is log. The y-axis is logged, the x-axis is not. Moving further, another type of relationship is just switching that, instead of a to the x, it's x to the a. This is called a power law. It's also a nonlinear relationship, which we can also linearize by, again, taking the logs of both sides. And in doing it step by step, you can see that we end up with the exponent, in this case, just as before, actually maintaining its same value, but now x is also a logged value. So with a power law, just switching it around like that, we have the log of x is linear in relation to the log of y. So we have to transform both of them, as you can imagine. So here we go again. Here is a curve established using that function. And in order to straighten it out, so to speak, we have to take the logs of both x and the log of y numerically to come up with a numeric transformation. Again, we have the same problem of, what is that 0.8 mean down here? So let's use graph paper. In this case, we're going to use log paper instead of semi-log paper. And so again, now we have graphing paper that is logged on both sides. This can easily be done in Excel. You just double click on or click on the axes, and up pops the options, and you pick log and allow it to do the log. But you should understand that you are, in a sense, graphically transforming something that is inherently linear in its logged values, if that makes sense. It's the graphical transformation versus the numeric transformation. The one on the right here is good for just graphical comparisons. You may want to apply the one on the left because the linear regression associated with this may be applicable, and it's going to involve the log of x, equal somehow to the log of y.